Hello, everyone. Welcome back. Today, we're going to be talking about the properties of vectors. Okay, so we're going to start with the cumulative property, then the associative property, then the distributive property, and then even more great properties. So let's get going. And these properties are not just to be memorized, these properties are also to be used and expanded upon as we work throughout this. So the first property is called the commutative property. And basically, the commutative property says that vector A plus vector B is equal to vector B plus vector A, right? So basically, the addition of vectors holds true to the same property as regular addition, right? If I have A plus B, that's equal to B plus A with any A and B, right? 1 plus 2 is the same as 2 plus 1, right? And so it's the same way with vectors. If I have A plus B, here I have vector A plus B. And then here I have vector b plus vector a. And as you can see, they're the exact same vector. Now, yes, they start and end at different places, but remember that vectors are only characterized by their magnitude and their directions. They're only characterized by how long it is, which is magnitude, and then by direction, so which direction it's going, and it's going in the exact same direction either way. And so, therefore, this property holds true. Okay, the next one is the associative properties. The associative property states that if we have something like a, oops, the associative property states that if we have something like vector A plus vector B plus vector C, this is equal to vector A plus vector B plus C in brackets like this. This is also equal to vector A plus vector B in brackets plus vector C. So in other words, it doesn't matter whether we add A and then B then C, or whether we add A and B first and then add C, or if we do B and C first, then add A. Either way, we're going to get the same thing, right? Because let's think about this. If we have over here, we have very clearly vector A plus vector B plus vector C, right? If we do it like that. But what if we were to do vector A plus B, so here, and then vector C? Well, there we go. We'd still have A plus B plus C. What if we were to add B and C first? We were to go here first, right? Vector like this first, and then vector A. We would still get the same thing, right? It would still be the same thing when it comes down to the magnitude and the direction. And so the associative property holds. Now, the distributive property, this also holds when it comes to vectors, right? You're probably very familiar with this from maybe middle school, maybe around grade 7 or 8, I think, where we have the distributive property with regular numbers that states that if we have something like this with regular numbers, we can distribute through. And the same holds true with vectors, right? Here we have A and B. And so A plus B would be, our resultant vector would be this one here, A plus B. And then here, same kind of thing, right? We have 2A and 2B. This would be 2A plus 2B, right? Now let's say we were to do this vector again a second time, A plus B again, so 2 of A plus B, A plus B plus A plus B. Well, look, we get the same vector as over here. It's saying that it's the same thing. Now, what else do we know? We know that if we have any vector and we add the zero vector, we get that same vector back because a zero vector does not do anything to the vector. If we have a scalar m times a scalar n times any vector a, this is the same as m times n times vector a. And likewise, if we have m plus n, right? So these both being some, a couple scalars times vector a. This is the same as m vector a plus n vector a. So these rules also still apply. Okay, so those are just some other properties we should keep in mind. So now using those properties, we're going to be able to we're going to be able to use these properties in order to answer the following questions. So here it says, given the rectangular prism, determine a single vector for each of the following. Find CD plus DB plus BA plus AC. Okay, well, let's think about that. First of all, I'm going to draw what that all looks like. So CD, DB, BA, BA, AC. Well, looks to me like this is the zero vector, right? Right? This is the zero vector. This is just equal to our zero vector here, right? All we did was we went in a whole square and we got back to where we started. So it's the same as that. All right, what about this next one here? Oops, meant to erase. How about the next one here? We have GE. So let's see, GE is like that. What about EA? It's like that. What about minus HF? Well, HF is up, so FH would be down. So it would go down like this. Ooh. So this is the same as just going from here to here. This is the same as vector GC, right? They're the same thing. All right, now let's try the third one. So the third one says, there we go, negative BA, so that's really AB, starting from A going to B, plus AE. Well, what's AE? It means it's going that way, so over there, plus FH, which is going down, plus HD, which is going over here. So what we really did is we did what? We went from A to B and then A to D, or we could say we went from A to C and then from C to D. Okay, so I'm going to use the first one. I'm going to say this is the same thing as AB plus, let's see, AB plus BD. Now they said this to actually determine a single vector for each of the following. Okay, so they just want a single vector. They don't want multiple vectors here. So that's interesting for this one. I guess if we were to determine a single vector, we could say vector, it's not really part of the line, but we could say vector right from A to D, because that's essentially what we did. So we can say equals vector AD. And let's think about how the properties support that, right? Here we have AB plus BD, right? We're going from A to B, then from B to D. If we add those things up, it's just adding up. It's just going to those same places. Okay. This next one says to prove that BD equals AE minus AB plus GH minus CA plus GC. Okay, so what I'm going to do here actually for this one is I'm going to define some vectors, first of all. And actually this, I should mention, this goes with the picture up here, not the pictures down there. So I'm going to define some vectors here. I'm going to say that this vector going like this, I'm going to define this as vector C. I'm going to define this as vector B. And I'm going to define this as vector A. So I'm going to define a couple vectors on there. And now I'm going to say, well, what can we do to prove that BD is equal to AE minus AB plus GH minus CA plus GB? So let's do that. Well, first of all, something I noticed here is that here we have AE subtracting from AB. And one thing we know from our properties is we can always switch things around in order to get what we would like to get, okay? And we would be better off if we switched a couple of these things around. So I'm going to say, okay, well, AE is really this one, right? And that's the same thing as what? That's the same thing as CG, right? That's the same as this one. So I'm going to switch it to CG. So CG minus AB plus GH minus CA plus GC. So that's going to be my first step. What can I do next? Well, I can say here we have CG plus GH. Well, this is what? This is the same thing as CH, right? We just end up at the same place, much like this one. We just end up with CH. So here we have CH minus AB minus CA plus GC. Good. Okay. Now, are there any other ones like that we can do? Well, what if I move, we have here plus GC and then here plus CH. So this is really just GH, right? So let's do that. GH minus AB minus CA. And then here we have minus AB minus CA. So what would that be equal to, right? Minus AB, which is really just BA, plus over here AC, right? So then this would just be BC, right? GH plus BC. That's what we have there. Okay, so let's take a look back over here as to what we have. Well, we're going to have GH, which goes over here like that, and then BC, which goes like that. Okay? All right, so what is GH the same as? GH the same as AB, right? So AB plus BC, and that's equal to AC. And AC is this one, right? This is from here to here. That is the same as BD. So we have proven now that it's the same. Now, I do want to mention there's many ways of solving this, right? If you prefer to use these variables, or sorry, not these variables, these vectors, define your vectors and use those, you can. You can also use just the letters such as this that I've been doing. Actually, all of these technically, I should have put a vector sign on all of them, so I will do that now. But yeah, but basically there's lots of different ways to go about it. There's lots of ways to approach this as long as you use these skills that you know in order to solve, then you're good. That's the main point here. Let's talk about this one. Let's prove that ED minus EF plus FE plus AB plus BF plus EC is equal to the zero vector. Okay, so how are we going to do that? First of all, let's see if we have anything that could kind of combine us a little bit. So here we have ED and EF. So of course that's going to be just the same as DF, right? Because we can say, if we like forwards vectors better, we can just say, okay, well, this is equal to ED, oh, not DE, whoops, ED plus FE plus FE again plus AB plus BF plus EC. Very good. Then we can say, okay, well, here we have ED, right? So from E to D. And then here we have from F to E, right? So what is this really, right? What is this really? This is really just, F to D. So we can just say, okay, F to D plus F to E plus, let's see, AB plus BF, that's just plus AF, and then plus EC. Okay. Now we can combine these two and say this is just FC. So we have FD plus FC plus AF. And then we can combine these two and say, well, this is just AC. So we have AC plus FD. And now we can look over here and see, well, AC is equal to what? AC is the same thing as DF. So then we have DF plus FD, which is the same as DF minus DF, right? Because we swap those around and swap the sign. And then we get the zero vector. So there we have it. We just ended up with the zero vector as expected. So basically, we need to use, our logic and what we know, and then also use these diagrams to show what's what. And that's why these diagrams are so important to have, because we need to know where each point is so we can determine where each vector is. So that's very key there. All right, well, that is everything for today. In the next lesson, we're going to be talking about vectors in 2 space and 3 space. So we will see you for that. Bye, everyone.